everybody. Welcome to today's webinar. My name's Robert French. I'm an applications engineer here at GoEngineer, kind of our CAM expert as well, down in the San Diego office. That's the branch that I'm out of. Obviously, GoEngineer is kind of all over the West Coast, headquartered in Salt Lake, but we're up and down the West Coast of California and most of the Pacific West. So. Welcome to today's webinar. Once again, we're going to be doing some introduction to 5-axis programming using CAMWorks. This is really just kind of baseline entry. A lot of people are intimidated by 5-axis programming, so kind of today's webinar's purpose is to show you that there's not a lot to it. We can do some pretty cool stuff with the 5-axis with just a little bit of knowledge and a little bit of a walkthrough, which I hope to provide here for you today. So. Kind of going over the basics, all the fundamentals that you're going to need in order to do your 5-axis programming. We'll walk through a couple practical examples, and if anybody has any questions at any time, feel free to ask those using the chat box there, and I'll address them if I can at the time. Otherwise, we can answer some of the more in-depth questions towards the end. So be sure to let me know if you have any questions, and you can also see my email right there. Go ahead and email me any questions later on if you have them. And we will be posting this video online, so you can always watch it again in the future on YouTube. Let's jump into it. So just real quickly, just giving you guys kind of an overview of the different CAM packages that we would offer. So here in this little spreadsheet, we see a couple columns and then list items on the left-hand side there, the different kind of functionalities or modules in a sense of what's available. So the first column there is the SOLIDWORKS CAM column. If you're on subscription in 2018, you actually have access to that first yellow column, the SOLIDWORKS CAM, and we got a lot of resources for that on YouTube and stuff, and that's included with your software if you're on subscription. So try to take advantage of the CAM software, but we don't stop there. We obviously go all the way up to CAMWorks Premium, which is the far right column, which is essentially the only package that would give you the functionality I'm going to show today. That last line item there, the 4 and 5-axis simultaneous milling, is kind of what we're focusing on. So top level package there on the right hand side that pretty much gives you every single thing that CAMWorks would offer. Alright, so when we're doing 4 and 5-axis programming, I just feel the need to bring up that we can't skip our fundamentals. People think it's so advanced that it's kind of in its own different world. It is in a sense, but we can't overlook kind of the simple 2.5-axis, 3-axis kind of steps that we take normally. Just really fundamental stuff. First off, starting with our machine definition. What machine are we choosing in CAMWorks? Obviously, you need to make sure that that's configured to 5-axis, and need to even go further and really start to set up our different axes and rotational axes and things like that. Identifying a coordinate system. So this is something that we isn't always required in CAMWorks, but I really hate that terminology or that phraseology. To me, identifying a coordinate system, you should just always be in the habit of doing. It's not needed for every little aspect of even simple programming or advanced programming, but might as well go ahead and identify it and avoid any potential pitfalls. It takes only a couple seconds. So I really try to establish that as something you always do in CAMWorks, regardless of what you anticipate you might be doing, or just always identify a coordinate system. And then lastly, putting the mill part setup that we program some of these complicated features. Just kind of putting the mill part setup that they're identified in as our home position on our machine, as 0, 0 on our rotational and tilt axes. Alright, so in order to do multi-axis programming or multi-surface programming, 4 and 5-axis simultaneous, we need to use the multi-axis mill operation. So once again, it's the only one that can program in the 4 and 5 axes. It's the only one that has the extra options, parameters, tabs that can facilitate these more complicated toolpaths. It can only be applied to multi-surface features, so we're not in the 2.5-axis, 3-axis feature definition realm anymore. Typically flat bottom pockets is what we mean when we say that. we need to identify a multi-surface feature, meaning we're not identifying a volume anymore. If you're familiar with the CAMWorks workflow, we're really choosing directly on surfaces and faces of our parts. And we can use it on the simpler features, and I've seen that done to just kind of, rather than having all these different features identified and just having a huge feature list that you have to program everything over, you can actually use the multi-surface feature to identify kind of the simpler 2.5 axis features, so you can get, these continuous tool paths. You're not lifting the tool off up to clearance and switching tools or switching kind of parameters between different features. Now you can identify them all as one feature, use a multi-axis mill operation on them, provided they're identified as a multi-surface feature. All right, so a little bit more into the multi-axis mill operation. So once again, I kind of mentioned earlier that a lot of people find this intimidating simply just because you're jumping into two additional axes, and there's a lot of rotational and relative motion going on, and as a result, the options become pretty extensive, right? We see here the multi-axis mill operation compared to just say a rough mill or a contour mill operation. We've got dang near double the tabs going on, lots of options with each one of them, so it gets a little intimidating at first. So I like to kind of consolidate that or kind of reel back our expectations and really just try to focus on a few key areas here to get a good tool path. Axis control tab is going to by far be your most important. This is really getting into specifics about what's the axes that I'm allowing the motion to happen in. What am I even doing a full 5-axis program? Do I really need to in my axis control tab, I really need to match what I'm trying to achieve in the real world with the options in my software. Try to not let the software have as much free range motion and do got to kind of curtail those, bring it in, really lock it down and control what we're allowing our machine to do. And that's all done within the axis control tab. Then we'll jump over to the pattern tab. Once we kind of lock down the motions that we're going to allow our machine to take, let's kind of develop the pattern or the tool paths directly on the surface. How are we going to see these tool paths flow and actually produce tool path on our part? Then we have the links tab. Sometimes we see on interrupted surfaces or complex surfaces that the tool wants to pull off of the surface, kind of retract a clearance, then re-engage somewhere else on the surface, when our goal should really be to keep that tool down, keep it on the surface, keep a constant chip load, constant feed rate, and really achieve a good surface finish on whatever we're trying to cut. And then lastly, making sure the tool is entering and leaving our toolpath area, safely and efficiently. Want to make sure we're not coming in and gouging, making sure we're, retracting correctly and not crashing as well on that side. So those are really the 4 tabs that I focus on, and obviously lots of other options in the other tabs for really refining your toolpath, but these 4 are the ones I like to focus on when I'm really just trying to achieve, like I say, a good toolpath on the surface, not a lot of retractions, not a lot of interrupts, keep a constant chip load going, keep the tool moving, keep it on the surface. All right, so let's actually jump into the software now and take a look at a couple practical examples. So I'm going to start with this kind of just spherical shape. So I'm in my CAMWorks, or I'm in SOLIDWORKS, and by extension CAMWorks, obviously, because CAMWorks is integrated right here inside of the software. A lot of different ways you can use your workflows. Obviously, we have our CAMWorks tabs up here on the command manager and our different tools within there. You can totally work off those tabs. I've just kind of gotten used to it over the years that the way I work with CAMWorks is right here out of the CAMWorks trees or the CAMWorks managers, right? Feature tree, operations tree, and tool tree. So obviously starting in the feature tree, like I said, we can't skip the basics. Got to focus on our machine definition first. So all these different machines we see listed here are configurable in the tech database, and if you've got different machines on your shop floor, obviously we recommend going into that database, really identifying those machines correctly and being accurate and diligent about the way we define them so that we have the best best chances, set ourselves up for success, that when we take our programs out to the shop floor, we have good confidence in whatever we're spitting out, whatever we're posting out here. So first and foremost, we want to make sure we're switching to a 5-axis machine. So once we're on the 5-axis, though, we're not quite done. There's a lot of kind of nebulous information now to the software about which axis is pointing which direction, what am I allowed to rotate about. So after we choose our machine, and we can configure, like I said, a lot of that data in the tech database, something we can't necessarily configure is our coordinate system. And like I said, always define a coordinate system. And no matter what we do with machine configuration, we can't get around setting up a correct coordinate system within the software. That's going to kind of just be unique to each part. So once I go ahead and identify the coordinate system here, and actually by default this guy just kind of works out for me, Z going upward, X and Y, kind of on my tabletop. So I can just hit check mark there. Now that the coordinate system's identified, you could also do it here in the property manager, or the CAMWorks feature manager. This was kind of a nice addition that they've started doing recently. The coordinate system kind of used to be hidden in the tab I see here only, but now it's been also moved to the feature tree manager, which is really helpful. It's kind of hard to miss now, and really good for my workflow where I just kind of work top to bottom here, and it's hard to miss in my chain there. So once it's set to 5-axis and we've got our coordinate system, we jump into our rotary tab just to make sure that our rotary axis is revolving around, our rotary motion is going around the correct axis, and that looks good to me. And then also the same thing for our tilt axis here. You really need to make sure that those are set up correctly so that your machine is aware what axes you're rotating around. All right, next step here would be to create the mill part setup. Like I said, this will just be kind of the 0 position. Obviously the mill part setup is constantly changing. Normally when we're in 2.5 and 3 axis, the mill part setup kind of implies this is the way that the part is fixtured in the machine, and it kind of can't move from that, and it's kind of locked down because we don't have any indexing available or any other motion besides XYZ. But in the case of 4 and 5 axis, we want to make sure it's kind of the 0 position, where the axes, both X, Y, and Z, and the rotationals A, B, and C are all kind of at their 0 position. So I check mark there, got my mill part setup created. I'll throw a multi-surface feature, right? We have to be using multi-surface feature. And typically when we do multi-surface feature, I'm a big fan of using the all displayed or other selection methods rather than clicking everything individually out here, because you might have tons of surfaces, but this is kind of a dream part where we only have one surface we need to select, and that's sufficient. So I check mark there. Now I've got my feature created, so just kind of reiterating some of the fundamentals of CAMWorks. Features first. We got to identify features. Everything kind of stems from the feature. We call it feature-based software, feature-based CAM. So identifying that feature is important, and we do it parametrically, right? We chose right on the SOLIDWORKS face, and that's the one of the biggest advantages to CAMWorks is when I go back to SOLIDWORKS and I actually change my design here, because my CAMWorks feature is based directly on a SOLIDWORKS solid body, I have a lot of parametric updating that happens. I could change the size of this sphere and see my feature update in CAMWorks, and by extension my operations update in CAMWorks as well, and my toolpaths eventually. So let's start programming this feature out though. I'm actually going to start with an area clearance just because it's hard to see a good simulation of this guy unless we got an area clearance going on it. Use the biggest tool possible. And so I'm just going to kind of leave this guy as basic as possible, maybe reduce the Z step over, but we're not too interested in this guy. That's why I'm not spending too much time on it. This is the just area clearance, right? And we're looking more for some of the simultaneous 4 and 5 axis, whereas this is just simply a 2.5 axis toolpath. So I'm going to increase my step over a little bit just to make this guy go a little quicker. Let's generate the toolpath for him. There we go, looking pretty decent just for area clearance. Now let's go back and start to do our complicated 4 and 5 axis simultaneous. So once again, the only operation that can provide me this functionality is the multi-axis mill. And you'll only see this option for a multi-axis mill operation if, only if, it's a multi-surface feature. So let's add the multi-axis mill. I'm going to go with the biggest ball nose, kind of finishing tool that that I have in my tool crib. All right, so here we go, jumping in to the complicated multi-axis mill operation parameter. So lots of tabs, gets a little intimidating. As I said, we're always kind of starting with axis control tab. That's always where I start, because we need to be very specific here about how many axes are we actually allowing in the motion of this toolpath. It's not always true that on a multi-surface feature that, oh, we've got a 5-axis machine, just let all 5 axes have at it. In this case we are, but that's why it's important to jump to this tab first and really kind of, don't let your machine run wild. You need to exert some control and some intelligence over it and really, specify what you're trying to let it do. So before I go too much further, I don't like to change too many settings. I feel like that's a mistake a lot of people make, is changing a whole lot of settings on a very complicated toolpath and then trying to, have expectations about what they see in the preview. Well, there's a lot going on. There's a lot of, information that's working with each other, that's all kind of working towards one goal. And the more you change, it's harder to understand, what is causing that change in my toolpath. So I tend to try to change only 1 or 2 things at a time and then analyze my toolpath and really try to understand what each setting is performing. And a lot of times with these toolpaths, they take so long to generate that I really recommend turning down your cut amount. We want to, keep the toolpath a little bit spaced out. The tighter we do our step over here, then the longer it takes to generate, and we're still really just in, the initial phases of this. Let's keep our step over broad, just get a general idea of what the toolpath looks like, kind of narrow that in, and once we get it looking good, that's when we can finally come in and really tighten up our toolpaths and really let the machine kind of sit for a while and take the couple minutes to generate this really complicated toolpath. So before we go much further, let's take a look at the toolpath. So not terrible. We've obviously got some issues with our retract and moves between different cuts. Right, our clearance plane isn't set correctly. And for those that aren't aware, blue is our cutting toolpath, red is kind of our rapids between those toolpaths. So the toolpath on the surface in general doesn't look too terrible. It might not be the best way to cut this particular part, but at least we kind of know where we stand at this point. So I'm going to jump back in. Something I'm not a huge fan of is, just the cutting style right now. We're kind of going one direction, and the sphere will kind of look awkward with scallops only one way. So in order to control that, right, axis control looks good right now. I mean, if we take a quick look at a simulation of this guy, and obviously it looks a little funny because we don't have the area clearance happening before it, but doesn't look too outlandish. The tool is kind of being continuous in one direction. It's not jumping around or anything like that. So I'm okay with that for now. But let's see if we can make it a little bit more of a spherical toolpath, right? This is kind of an XY toolpath on a radial part or cylindrical part, polar part, if you will. So I'm going to jump to the pattern tab. And right now our issue is we're on slice. If you look from the top down, it looks like it's being sliced, just kind of simple XY toolpaths. We can do something a little bit more clever, such as flow line or offset from surface. We're essentially going to choose a surface and kind of take that surface and create a bunch of different offsets. Like we're copying that surface and placing it, every so often. And every so often where those additional surfaces cut through the part is where we'll place additional toolpaths. So we've got once we change to offset from surface, we identify a surface. Got to create a feature for it. This bottom face, check mark. Now that surface feature is created, I check mark it. That's the surface I'm choosing here. And let's take a preview of the toolpath. Right, so we've essentially taken that bottom surface and created an offset surface from it, at a specified amount going upward, and then now the toolpath runs along that. So looking a little bit better, like a toolpath that makes a little bit more sense for this part. What I'm still not happy about is, the way the way the tool is lifting off the part, and obviously we still have some issues with our entries and retracts. So these issues between the tool lifting off is simply because I've set offset from surface, but now down below where I've said zig, I'm really only letting the tool move one direction. I could go zigzag and let the tool kind of work back and forth, and that might keep it down on the part, but might as well go the next step further and go to spiral, which is essentially like zigzag, but on a, is like zigzag, but on a round part in some cases. So I'm going to switch to spiral here, and now take a look at my toolpath. And I really get, kind of what I was looking for earlier, what I described earlier, which is the tool staying on the surface and really keeping a continuous cut going. There's no more excessive lift-offs, coming off and leading in and leading out, back off the part, back onto the part. So staying continuous, staying on the surface. My only issue now, that last bullet point I mentioned, we want to jump into the entry retract tab. And right now our clearance plane is 2 millimeters from our origin in Z, which is not enough to make it out of this part. I already know ahead of time the size of this part. I'm going to go ahead and say, go about 150 millimeters up, about 6 inches. Now it's looking really strong. One other quick thing I'll do here, just so we can kind of see a little bit of this toolpath in action. A lot of times when we're simulating, we don't want to see all the steps of the simulation. In this case, I'm really just interested in this multi-axis mill simulation, but when we simulated that before, we don't have the area clearance done. It looks kind of awkward. Little trick here is if we hold down Shift, right-click the operation we want to see and say simulate, we can say, well, start the simulation from the point of the area clearance or any other operations being done ahead of time. Now, it takes it a second to calculate, but eventually when we start our simulation here, we'll see kind of the rough mill or the area clearance already performed on this object. Not to the best of resolution, it kind of just cheats and goes as quick as it can, but a much better place to start to analyze this multi-axis mill. Just keeping the tool on surface. My step over amount's still a little too big, obviously, but that's an easy number just to type in and fix. But I'm really happy with this toolpath. The tool's staying down. I'm seeing continuous motion, jerking and moving around of the tool itself. It seems like a very constant motion. We won't let that go all the way through, but we'll do a quick compare, and we can see that we're getting on size pretty well. Once again, the only thing we'd have to really do is refine our step over amount. Cool, so I got a couple other example parts. We're getting a little tight on time. That's my apologies, but let's see if we can get a couple other things here programmed. Show you a couple other of my favorite kind of toolpath types. So here we got a surface, right? And we can program off of surfaces, solid bodies, whatever. So I've got this kind of curved surface, a little bit of waviness to it, if you will. So once again, let's go through our steps. Don't skip anything. Let's make sure we're on a 5-axis machine. Jump to our Setup tab. Make sure our axes are pointed in the correct direction. Let's actually say Y is going that way. Let's flip it. There we go. Z upward, Y and X. There's our coordinate system. Let's jump to our rotary and tilt. Make sure those are good to go. Rotary about Z, tilt about X. Looks good. Let's add our mill part setup. That's the wrong direction. Let's go ahead and make the 0 position right here, but upside down. Let's go ahead and reverse that. Let's add our multi-surface feature. Simply just going to be a one-face selection once again, but like I said, when you're dealing with more complicated stuff, you can use all displayed or different selection methods that are a little bit quicker. Let's add our multi-axis mill operation. Let's go with our biggest ball nose. All right, so let me show you a couple other things that I'm a fan of here. Once again, we'll leave it on 5 axes. Let's jump to the pattern tab. We're on slice. That's good. And let's just see what we got before we go any further. So not looking too bad. But let's say, for instance, that I'm not happy with this direction. I want to kind of go 90 degrees to this. Slice might work for me, but let's go 90 degrees to this direction. So that's under the pattern tab. We are on slice, but our cut angle, we're going to flip 90 degrees. And that's looking a little bit better, going the direction we want. We've still got a lot of pull-offs going on. We've got kind of these interrupted cuts on the side here that I'm not a huge fan of. So the toolpaths are staying nice in X, Y, and not necessarily following the edges of the feature very well. So that's when I jump into the pattern tab once again. And slice almost worked out for us. But this is really my other favorite type. This is one I use very, very often. Flow line between curves. We'll identify, much like offset from surface or offset from curve, we identify different curves, and we're going to kind of create our toolpaths between those two. So this original feature was created with 4 sketches total, one on the left, one on the right, one on the back, one on the front, and a loft command. I'm going to grab sketch 1 as the first curve, and I see that kind of highlighted over here on the left with a blue line. And then for my lower curve, I'm going to choose the opposite side. Right here, and we can see the blue line on that side. And now with flow line between curves, we'll see this right edge get cleaned up a little bit where we're not coming off the part anymore. It kind of morphs the toolpaths to wave between those two edges, and we see kind of nice clean toolpaths following the edge on this side, no longer kind of stopping short as we draw these kind of cookie cutter lines that intersect the surface in an awkward way. Last thing I might do here is if you're allowing kind of conventional and climb cutting, you can say, I don't just want to zig, I want to zigzag. I don't want to see all these excessive pull-ups happening. So we'll say preview after zigzagging, and we can eliminate all of these different entry and retracts and really keep the tool on the surface cutting the whole time, going back and forth. One last thing I'll show you guys. I had a couple more, but we're getting a little tight on time, and I do want to be able to answer a couple questions. We can hang out a little longer than the 30 minutes. Is this part right here. So this part right here is a great example of we might have 5 axes on our machine, but we don't necessarily need all 5 axes on our machine. Let's go ahead and set up, though, that we are a 5-axis machine. We'd set up our coordinate system, and a lot of times it can be helpful in SOLIDWORKS. Knowing SOLIDWORKS is a big help in CAMWorks because you can use things like sketches or offset surfaces or extended surfaces to kind of help facilitate and modify and amplify your toolpaths or your feature definitions and then your toolpaths. So let's define our coordinate system. Let's get Z going upward using this sketch line right here. I can reverse that guy. Let's get X going the other way. Cool, looks good. Be happy with that. Make sure our rotary and tilt axis, tilt axis doesn't look good. Let's put that about the Y axis. There we go. And now we can identify our mill part setup. Remember, this is kind of the 0 point. Be happy with that. Multi-surface feature. Identifying going around here. Probably could have done all displayed in this situation, but either way works. Cool. Ooh, did I miss an edge? I did. That's why all displayed works better, so you don't miss those little surfaces. Check mark. Let's add our multi-axis mill operation. This is where I was saying it's not always required that you throw all 5 axes at a particular feature. In this case, underneath my axis control, I'm going to switch to 4-axis. And I'm going to make sure that I'm rotating about the y-axis. Otherwise, when we look at, letting it rotate around the wrong axes, we start to get all kinds of interesting situations. So you'll see right away that axis control can fix some of your biggest problems because Z is obviously not correct. If we zoom in a little bit, we can see that that's the y-axis. We want to go about the tilt, not the rotary. So we highlight y-axis, we say preview. We already get a way better toolpath. Last kind of idea here with finishing and ball nose mills end mills is we typically don't want bottom dead center of a ball nose end mill to be doing the cutting action or be what's driven on the part. And that's what's happening right now. This line is literally the end point of this ball end mill, bottom dead center, which if you're a machinist know doesn't have any speed on it. Right at the middle of the tool, there's no cutting edges, there's no cutting speed. So we typically want to tilt the tool back and forward a little bit. So right here in the axis control is where we can come in and add things like lead at lag angles. So you can throw something in there like 10 degrees, kind of have the tool tilt back for you. Say OK, generate some toolpaths, and once again this might look a little funny because I don't have an area clearance. I apologize, a little strapped for time. Tool might be a little big as well. But you can see it coming in there, rotating around the part with just a little bit of lag angle in it. It's not quite bottom dead center of the tool that's cutting. You can see it's offset there slightly. So I had a lot of other things I planned to show you guys, but we are a little short on time. Happy to answer any questions anybody has, but that's all for the official presentation. We'll be posting this video online. Remember, you can always hit me up with questions if you have them, and if anybody wants to hang around a little bit more and see some more stuff, I'm happy to help with that as well. But that does it for today. Thanks for coming, guys. Hey all, just a quick addition to this webinar. I did mention that the links tab being important, and I didn't get enough time to cover it, so I wanted to jump into that real quick. We have two different types of links. We have links along a cut, and so along a cut would be kind of the transition from, you know, this shelf up here, these paths up here, down to this lower shelf. And right now you can see we're kind of retracting to clearance and coming over. Then we also have the links between cuts. So between cuts would be kind of, you know, how does it transition from one of these paths over, you know, left to right here to the next path. So in the links tab, we have kind of a section for both of those, the links along cut and the links between cut. We can set a threshold for each of those that's either percentage based or pure distance, and we can treat our links differently when our links along the cut are bigger or smaller than that. You can see kind of the less than or equal to symbol and then the greater than symbol. Once again, that's for both along the cut and between the cut. So right here along the cut, it's kind of awkward to transition up there. Maybe we've already got this kind of shelf in the middle cut out. So rather than doing a retract to clearance, I could do something like along cut. Let's, instead of retracting to the clearance, right now this gap that it's going along is bigger than the 100th thou threshold. So when it's bigger than the 100th thou threshold, instead of retracting to the clearance, let's go direct. And take a look at the change that makes. So a lot quicker, keeping the toolpath down. Once again, that really only makes sense if we already had this middle shelf cut out, but maybe that's the case. Now additionally, we have links between the cuts kind of being awkward, retracting to clearance. So let's jump in there and let's say, depending on, I'm not sure what the size of the gap is, but let's just change both of these to direct then. And now we're going right through the part. And that's a product of my type of links, and because I'm saying a zig type underneath my pattern. If I change that to zigzag though, that combined with a direct link between passes can produce something pretty nice. So links is an important tab about, you know, preventing your tool from doing a lot of these retracts and you know, kind of excessive moves, whereas, you know, kind of one of the focuses of this webinar was to try to keep the tool down, keep it on the surface. Links is a big part of that, so yeah, that's it.